This video will cover pages 5 and 6 of the first day packet. We're going to just briefly cover the skill and drill of writing intervals in interval notation. So most students are comfortable using inequality notation, using less than or equal to symbols, less than symbols, and drawing intervals on a number line. So we should also be able to write them in interval notation, which is more common in the calculus sequence. So let's start with this example. We're going to first draw the interval 6 less than x less than or equal to 17 on the number line and also write it in interval notation. So we see there's a strict inequality. It says 6 is strictly less than x. You indicate a strict inequality with an open circle. So the low end of the interval has an open circle at 6, and at the top end of the interval it says x is less than or equal to 17. So up here we indicate that with a closed circle at 17 to say that x can equal 17, but x cannot equal 6. And then I'll just shade in all the x values in between. So this interval representation here is saying x cannot equal 6, but it can equal any number between 6 and 17, and it can also equal 17. When you write an interval in interval notation, you first start with the low value, 6, comma, the high value, 17. We use a parenthesis to indicate strict inequality. So this case it's strict less than, and we use a bracket to indicate that it can equal that value on the end. So in this case it's this less than or equal to with a bracket. So here is the interval notation, parenthesis 6 comma 17 bracket, 6 up to 17. Let's do another. So example 10, it says we're going to show 0 less than y less than 150 on this vertical number line. So again, it's a strict inequality starting at a low of 0. So here is 0, low end, and then it extends all the way up to 150, which again is an open circle. So the y value can be any number between 0 and 150, but the open circles indicate that it cannot equal 0 and it cannot equal 150. When we write it in interval notation, the low value is 0, comma, the high value is 150, and since it's strict inequality on both sides, we have a parenthesis on both sides. Example 11, it says that x is greater than or equal to 200, or you might read that 200 is less than or equal to x. So the 200 gets a closed circle because x can equal it, and you see that the x can equal it or be bigger than it. Now this time I shade all the way up the number line to indicate that it goes on and on and on, all the way up to positive infinity up here, 200 or higher. Again, when we write it in interval notation, you start with the low value. The low value on this interval is 200, comma. The high value on this interval is not a number, but it's infinity. It diverges up. It can be as high as you like. The 200, you can equal it, so it gets a bracket. But x cannot actually equal a number, infinity, so we use a parenthesis with infinity. You should always use a parenthesis with infinity or negative infinity. You can't ever equal the number infinity or negative infinity in the real numbers. All right, and then lastly, it says 75 is greater than or equal to y, or y is less than or equal to 75. Again, 75 gets a closed circle because it can equal it. And it says the y is less than or equal to it. It's smaller than or equal to it. So I shade below 75 all the way down. 75 and lower is the y value. All right, so this time if you think about what goes down here, this would be negative infinity. Down, 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 diverging down towards negative infinity. So when we write it in interval notation, the low end is negative infinity, comma, the high end is 75. So negative infinity, you can't actually equal it, so it gets a parenthesis. 75, it's a closed circle. It's less than or equal to, so it gets a bracket. There's your interval notation. All right, and just one last thing here before we go on to the day 2 content. Recall the domain of a function is the set of all x values that you can plug in to produce real valued outputs. The range of a function is the set of all y values that the function produces. So we can use that same idea with interval notation and shading intervals to help identify domain values. So here we have a function. This graph is meant to indicate that it's approaching the y-axis here. It's getting closer and closer and closer to the y-axis, but it's not actually hitting it. And up here on the right tail, it's going up at a slower and slower rate, but it is going up and up and up forever. This is actually what looks like a logarithm function here. All right, so the domain of this function, the set of all x's that this function produces. In order to determine this, we're asking ourselves, as we travel left and right, where does the graph exist? It might help you to actually draw a horizontal number line from left to right and imagine yourself walking it left to right and looking up and asking, does the graph exist where you're standing? So over here, if you were walking over here on this part of the real number line, there is no graph. These x values over here do not produce graph. But when you're standing over here, there is graph. So these x values do produce graph. So where does it start? It looks like the graph kind of starts right here. This is at x equals 0. And then after that point, there's graph, there's graph, there's graph, all the way up to infinity. If you walked this way forever to the right, there would be graph, right? Because this graph just keeps going and going and going. So all of these x values produce graph. All of these x values are in the domain, all the way up to positive infinity. On the left side of this interval here, we ask ourselves, is x equals 0 going to be on the graph or not? Well, I said that this graph gets closer and closer and closer to the y-axis, but it's actually never going to hit it. So the low end of the interval, where x is 0, is actually not in the domain. It gets a parenthesis. If you were drawing it on the number line, it gets an open circle. X cannot actually equal 0, comma, infinity is the high end. So the domain of this function is from 0 up to infinity, but you can't actually equal x equals 0. Let's do the same thing with the range. Again, if you're doing the range, you draw a vertical line and you imagine yourself walking up and down on this vertical line and asking if the graph exists. So when you're way down here, you see the graph exists down here. When you're here, yep, there's graph right there. And you go up higher, yep, still graph. You could walk up and down forever from positive infinity down to negative infinity, and there's graph, there's graph, there's graph everywhere. The graph exists for all y values. So the range of this function is from negative infinity up to positive infinity. The range of this function is all real numbers. Let's try example 14. Use interval notation to identify the domain and the range of the function. Let's start with the domain. Domain is a set of all x's that produce real valued outputs, the set of x's that produce graph. So again, I draw a number line left to right, and I imagine walking left and right on this number line and asking, does the graph exist where I'm standing? So over here we see this graph looks like it's just extending to the left forever. So if I walk down to the left, there would be graph down all the way down to negative infinity. And if I walk to the right, there's graph, there's graph, there's graph, there's graph, and there's an arrow on the end. It looks like it just never stops. From left to right, this graph exists forever. The domain would be from negative infinity up to positive infinity. It's all real numbers. The graph exists everywhere from left to right. Let's do the same for the range. Again, for the range, we're looking for all the y's that the graph produces. If you Imagine drawing your vertical number line and walking top to bottom. So there's definitely graph up here, right? Up on the top side, above the x-axis. But down here, below the x-axis, there's no graph. These y values are not in the range. There's no graph below the x-axis. So where does it start? It looks like right here at the x-axis is where we need to start thinking about graph existing. And that would be a height of y equals 0. So anything above that, it looks like there's graph. Anything above y equals 0, all the way up to positive infinity. Now this graph here looks like it's getting closer and closer and closer to the x-axis, but it's not actually hitting it. So it looks like the graph cannot actually equal y equals 0. It just gets closer and closer to it. So again, we would use a parenthesis 0 as the low, and then it goes up to a positive infinity with the high. And again, you've got to use a parenthesis because the graph never actually reaches a height of y equals 0. It just gets closer and closer to a height of y equals 0. All right, and lastly, let's find the domain and the range of the function in this graph. In example 15, left to right. Looks like this graph extends going forever and ever and ever left to right. There's no stopping. There's an arrow on both ends and it just keeps going and going and going and going and going to the left and keeps going and going and going to the right. So all real numbers would be the domain. From negative infinity is the low up to positive infinity is the high. And again, when we think about range, we're thinking about the y values it hits, the heights the graph hits. And again, it looks like it goes low, 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 down to negative infinity, up to high, 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 positive infinity, never stops, never breaks. So again, it looks like all real numbers is the range, so from negative infinity to positive infinity.